Oh, man. Okay. So I promise that we will come back to scheduling, but we're not gonna do it right now because I mean, first of all, because I did run out of time and I didn't go through the source code, and my understanding was partial. But second, one of your classmates did, and he understood it way better than I did, at least as of now, which is pretty. Yeah, do not, but there in the back. And so he went through completely fair scheduler and the patches, like essentially evolution of the scheduler, and why it actually like why those ad hoc patches which they tried to introduce stopped working at some point, and then went to this earlier virtual deadline. What is it called? ED? Earliest eligible virtual deadline for a scheduler, which is currently the default, replacing completely fair scheduler in the Linux kernel. So, but since it was a short notice, just a conversation today, we decided let's not rush it, but Yadunandan will come and like talk here for as long as he wants on Monday, by kind of guiding you through the source code, explaining for schedulers, right? So that's cool, right? So, and then we will like completely understand what's going on there in the Linux kernel and why they get stuck so much. But today I wanted to talk about something different. So I wanted to start talking about inter-process communication and access control in the kernel. So essentially, everything what we built so far is nice, but it's not really clear how to build a meaningful system out of it. Let me explain quickly what I mean. So imagine you're running this tiny microkernel which we built, and maybe we didn't build everything, but we're pretty close. And imagine now you say, look, I really want to build something like Unix abstraction on top of it, right? So you say, look, I'll have something like a file system, or even like a disk or / NVMe. NVMe, you probably know it's a PCIe attached SSD driver running as a process, right? Talking to a real NVMe device. On top of it, you might have a file system. You might have something like a network device driver, which talks to a network interface. And you might have something like a TCP stack on top of it, but maybe it's not necessary, and maybe each process will have its own kind of like a private TCP stack. The idea for this solution is that really TCP doesn't have to be shared. So sharing of the TCP stack in the kernel is just a coincidence, because there is nothing in the TCP stack which you share across connections. I mean, might argue. I mean, I'm not an expert at TCP, but roughly speaking, you open a socket and that's your private connection. So to some degree, you can say that, okay, I actually, if only it comes for free in terms of like isolation or something, then I will just run a private instance of a TCP stack per connection, right? Why is that? Because if something goes wrong and there is a bug in TCP, it connects it, like the whole thing might die, but you know, my application will go forward and will not even notice, because like one connection will close, but if I have 100 connections, 99 will stay. When I said, okay, there is nothing shared in TCP, well, there is a little bit of shared state. Like you can say, sure, there's like maybe ports. The port space are shared. Maybe you have to allocate out of this port share. But the reason I'm bringing it up is just that if TCP is inherently not shared, you can run like private instances of TCP. The file system typically is used as a shared thing, right? I mean, okay, what I mean here is if you have those processes like P1, or maybe T2, you typically they do share the file system, and you can again argue against it. You say, look, really these days, like on Mac OS, for example, or on something like Nix OS, the application itself is presented and essentially just runs on a private view of a file system. It cannot even access the whole file system, right? And so you can say, look, but maybe this argument could also be like a little bit relaxed and like really, like there is the possibility of running a private file system inside the application, and maybe you just share a very small subset of your home where you really like saving and like shared files, which you run this application, which whatever runs a snapshot of its own file system, but then shares with the whole. But for my kind of argument, what I'm saying is that most likely there will be some shared subsystems in this, and even if you run like private TCP stacks, eventually those guys, like if you say, look, these are two processes you want to do, they will be talking to this shared. This will be shared. This might be shared depending on how you structure the file system, but most likely multiple file systems might be running on top of a single disk, stuff like that, right? And that becomes your kind of your OS, right? So everything what you, again, if in the past you were pushing everything, essentially all of these components in the kernel, and if you take a look at the x86 kernel or Linux or FreeBSD, all of it was running in a kernel, and this was just a syscall interface. You do a syscall, you invoke something, right? And you reach this subsystem. In our microkernel system, we run it as a collection of processes. So all of these guys, they are a little special, but they're also processes, like they're whatever, process 3, process 4, process 5, process 6, right? And I mean, again, the story is not too far off from where modern operating systems are evolving, right? So if you follow Android, and I mean, like you ask me, do I follow? No, I don't really, but like once in a while when I look at it, they always have some user level services which run as processes, and they keep pushing stuff outside of the kernel. File systems run as part of this file system for user case framework use, even on Linux, right? So just because it's more reliable, easier to port, because it's much harder to port. Like Linux interface call, system call is way more stable compared to the environment of the kernel, which keeps evolving and slightly like changes. Essentially, like for different reasons, but and partially for security as well, running stuff in user level makes sense, right? We still, almost no one runs TCP as user level stacks. It still lives in the kernel. Device drivers still live in the kernel on most operating systems still, but there is still a push to push them outside and run them as microkernel processes, right? So with this kind of view, let me ask you a question. So do you kind of buy the argument that this construction or this architecture of the kernel is equivalent to what we have on Linux, for example, which runs everything in a kernel? Like essentially what I'm trying to ask is the following. Do you agree that you can construct a POSIX-like POSIX-like system on top of a microkernel in this way?
I can think of two things that might be more difficult. Firstly, how does a user process know about one of these special processes? How is it identified? A syscall is some global thing that has no process ID. It doesn't have to know which it's connecting. And then the other is, how do you do permissions? If it's not in the kernel, and those are also in user space, how do you keep it secure?
Correct. And this is exactly what I'm trying to get to. So there are like, and maybe I missed part of it, but or maybe I'm like misinterpreting roughly what your comment is. But there are two things. One is naming, because wow, in a Linux kernel, everything is fixed. The names are fixed. You always invoke syscall, and then you do. I mean, they're not specifically fixed. Syscall, and let's say you do read, saying that yes, I want to read a. So it's clearly goes to a file system, right? You already know from this name which file system. You don't know, because then you pass a file descriptor, and this file descriptor virtualizes like this namespace of multiple file systems, but you reach a specific file system. So there is a little bit of a naming hidden here, right? And moreover, so and in this system, like imagine you start a new process, the new for n, and you say like, where is my file system? Like, how do I know that I have to talk to this one? But second, what Talia said is also, what do you do with permissions? And because in Linux, I mean, the problem looks solved. The emphasis here is looks, because really it's kind of like mostly avoided, meaning that in Linux, in Unix systems originally, permissions and access control was only implemented for the file system, right? Meaning that if you have a specific user ID in a file system, you can access your own files and set in other files which allow you access as well, right? But for example, everyone can, for example, do a read system call, or everyone can do like a socket open or whatnot, connection open system call. And then Linux, at some point, they realized, okay, it's not really a good solution, because we want to create, like, for example, very tightly locked processes, even on Linux. And we don't want them to give them permission to execute any system or some system calls. So essentially, we want a way finer grain, way finer control over what is allowed, right? And Linux has multiple mechanisms. Sure, like it has a notion of a capability which says, okay, you can only invoke a certain service or function in the kernel if you have a specific capability, right? So for example, if we talked about scheduler last time, I think you can, in order to lower your nice, you need to have a capability in Linux, meaning you become more privileged in terms of nice. Nice meaning that your scheduling priority goes up. You can lower your nice, meaning you can say, okay, I want to become less privileged. But in order to, you can not lower, you can increase your nice, meaning that you become less privileged, because the lowest nice numbers, like -40 or something, are here. But you cannot do this transition, right? And it becomes a little ad hoc, right? You say, look, first we have this interface of capabilities, then Linux introduced this framework, which is called SC-Linux. SC-Linux is a collection of hooks. Essentially, imagine you have a function foo_bar in a kernel, and you somehow decided that this foo is security sensitive, and you want to control who can invoke it. So this framework is SC-Linux. They said, okay, we will introduce a collection of hooks, like typically on entry to the function, and maybe on the exit, but the rules might be slightly more complex. And at this point, it will consult your security policy if this SC-Linux is enabled, and ask the question against the policy: is this invocation allowed? And it looks like only flexible, because like essentially, if you have enough hooks through the kernel, and hooks meaning they're not dynamic, like they actually, I think they patch the code and like, because there are some corner cases, because there is something like if condition and you invoke a hook, but else you don't invoke a hook, something like this. So it was like a significant amount of manual labor to do this. And then you say, look, and I will write some kind of a policy saying that if I'm, for example, running my TVs typically run Linux as well. And you say, look, this process can do whatever. I'm not an expert making it up, but it cannot send packets, for example. Anything but sending packets, because that's kind of scary. And so your SC-Linux policy will disable invocation of those network-related system calls, right? So I mentioned capability interface. And capability is kind of like a subset of SE Linux, because capability has like a way smaller set of those kind of checks. And if a process has a specific like mask yes for this check, then it can pass it, right? If not, then not, right? And then it went on and on. Like people started saying, okay, when you see Linux is inflexible, so we're gonna be using what is this? What is it? Berkeley software, eBPF, right? So essentially a mechanism which allows you to eject pieces of code in the Linux kernel and do those checks. But let's just stick with these two, right? So here, sure, it does look on the surface, Linux kernel seems to be fine in terms of access control. In reality, it's not solved. And if you want to lock your kernel, you really have to do something like SE Linux. So for example, some meaningful examples can be like web browsers. Maybe you say, look, I'm running something sensitive within the web browser, and I really severely restrict the number of system calls or kind of system calls which this web browser process can invoke, right? So in practice, however, again, the solution is in Linux is very ad hoc. So writing those policies with the complexity of the kernel, and imagine it's 27 million lines of code or something like that. It gets kind of like elaborate. So there are people who made careers in just writing those C Linux policies, right? And you're never still sure, like, what's the high level guarantee? Like, can this process leak data or not somehow? And every other half a year, they discover a new way that there was some kind of map on top of a map, something, and you suddenly can leak information, right? And arguably, however, despite the fact that it looks that this microkernel construction is less friendly, it might offer a more conceptual solution to those security problems, right? So because if you build your system like this, then the fact that you can communicate with a file system or with this specific instance of a file system, because maybe we are so smart that we're running multiple instances of a file system and you might not be able to communicate with this one, gives you a notion of access control, meaning that like certain parts of the system are not reachable. And if you're clever enough, you can actually create processes which cannot reach anything. Maybe they can reach a network device driver, but nothing else. And there's simply no way to invoke a system call. And what kind of like changes in this kernel is that by construction, you start in a state in which nothing is allowed. And it's a little bit easier, arguably, although you can counter argue as well, lock or implement a specific information flow policy, meaning a high level, let's imagine you have a high level invariant saying that this process cannot reach the network. And you say, look, yeah, can it or not? And then you say, no, it cannot talk to a network device driver. Well, sure, but can it talk, for example, to a file system? Well, that's okay, but if the file system can talk to the network, then this process might not talk to the network only if the file system either is verified or you trust it not to relay messages from that process to a network, which we can say a guarantee, but at least it's explicit, right? That this argument makes sense. So it's like, essentially, think of it as like, essentially you have an explicit graph of what can happen in this system, right? And you say, look, you can maybe split islands like this, saying that these two islands are completely disconnected. Like this is user one, this is user two. And maybe if we very carefully construct this microkernel, we can even have a guarantee that these guys cannot affect each other, not only like through explicit communication mechanisms, saying that okay, there is no way to send messages, but for example, this guy cannot, maybe they even run like a separate instances of schedulers or never overlap on a specific set of physical cores, which gives us a guarantee that no matter how many processes this guy starts, maybe it starts like a 4 bomb here, right? It will never affect the other island, right? It's a pretty cool guarantee actually, and it's not like it's practical guarantee because if you're running a real car, like again, one of my PhD students got an offer from one of the car manufacturers. I mean, like the anecdotal stories, offers are not easy these days. For whatever reason, industry decided that they're gonna like bend everyone over. No one will get hired or will be hired with significantly lower compensation. So getting, and he is not yet graduated, right? So getting an offer is already an achievement in the modern world, which was not the case a couple of years ago. But the car companies essentially were willing to hire someone as a kernel architect, as a kernel architect to essentially work on this high level problems. Like, because if you have your GUI entertainment here, you have a very strong guarantee that your mission critical stuff, which steers the wheels, does whatnot for the car, will not interfere with the other part of the work, right? And this formally, this property is called non-interference. It's way more complicated than it looks, because if you allow those guys to share cores, then immediately you have to build a scheduler, which is somehow provides temporal isolation, which is like, even from last time, immediately becomes non-trivial. You say, look, no matter what happens in this island still gets a half of the CPU, for example, immediately or something, right? So that's hard. You say, look, let's partition the cores. Problem solved, right? Well, not quite, because those guys have like shared caches potentially. Or if the cores are logical hyperthreads, you can still like start running on conflicting on shared resources for the hyperthreads, right? So you have to partition physical cores, you have to partition caches. Then you have to partition memory controllers, because I mean it's harder, but still you can, probably affect behavior. The real problem comes in when you say, look, but really I need to like somehow let them talk on the network. And can you partition this one, and so on and so on. Like typically these guys start saying, okay, we can export virtual, it's called SR, single root IO virtualization, so essentially abstraction. A single physical device exports like a version, its logical version, kind of like virtualizes itself, and each network device gets its own version, own copy. Seems the problem is solved, but really there is some hardware here, some silicon, which processes those views from those like virtual devices, right? And then these become shared, and so on and so on. So, okay, achieving non-interference it's a tricky business, but at least you have a light, you say, look, at the end of the tunnel. So you say, okay, at least I start with the system in which nothing is shared. And if I'm lucky to patch the microkernel to make sure that this property of non-interference is somehow encoded, like, the CPU cores never overlap, caches don't overlap, I'm at least like somewhat moving in the right direction. If you think about how to enforce this property in Linux, it's almost impossible, because Linux, it has C groups and stuff, but there's a very soft guarantees, right? So
in that case, what if one node is shared by two subsystems?
One CPU?
One node in your class.
Good question. So, and for example, it can be this network interface, because you say, look, it's an embedded system, this interface cannot be virtualized, so we will really implement sharing like this. You can construct it, and at this point, at least you have explicit. It's not like you suddenly jumping in a monolithic kernel in which everything is shared, allocator is shared, everything is shared. You can still maybe, it's possible to design a microkernel which splits the allocator and memory partitions in such a way that, those guys, it has its own memory allocation, and they cannot at least conflict with memory. But in general, you face a question, okay, my device has to be multiplexed. So what am I doing now? Up until now, it was just blind trust. Essentially, you make this component as simple as possible. You carefully review it, and you say, look, I trust that there will be no leakage of data between those guys at this. Today we have enough, the verification tooling matured enough that you can actually write a mathematical proof that of non-interference. And again, in verification, everything is only as good as what is that you verify. You can see there will be no messages exchange between these two. Reasonably easy to verify, but going and saying, look, you cannot leak each other cache lines or each other TLB entries, way harder. So we're not there yet, but at least we like moving in that direction.
So, you've been talking about adding permissions. I'm familiar with a different model from OpenBSD, where it's removing permissions. You start with everything, and then you invoke a pledge sys12, which says what you actually need, and it subtracts everything else. And then you can iteratively do this after, like say you parse, and then you never need the file system again, then you can drop that permission. And then the rest of your program can't access them.
And in FreeBSD, if I understand correctly, and I'm not an expert, although this is the better model than in Linux, but OpenBSD, if I understand correctly, just a fork of FreeBSD, but many years ago, so it's the same kernel. So if I understand correctly, it's the same model as Linux. I can be wrong, and maybe they have their own kind of like whatever. Do you know the name of the like?
I know they call it pledge. But I know they added pledge after their fork. It's an OpenBSD.
Can be, but essentially, if I understand correctly, and I mean, like not an expert, but it's something similar. It's still a shared kernel, and with probably some kind of a framework of hooks similar to a C Linux, but for FreeBSD or for OpenBSD, and maybe slightly different framework, right? And then you say, look, if in order to invoke this function, I need an explicit permission. And then you start with a process which has none. And Linux allows you to write those policies as well and grant them dynamically and stuff like that.
I guess what I'm trying to understand is if you start with nothing and you're requesting more permissions, then what's stopping you from requesting everything? How is that secure?
Right. So like you have to solve it at the level of this policy. At some point okay, sure. Like a real world example, and it actually gets hard. So there is a community of people, and you never probably read the conferences or never read a publication from this community. It's I think it's called Access Control Community, right? So they essentially try to answer those questions even in real life. They have ideas that like real physical people might have those rights, like in a secured facilities or like in places like hospitals. They have ideas that normally you cannot do a specific action, but there is that idea of a break glass policy, kind of like say in an emergency, we're gonna at least give you this right, and you can like do whatever you have to do. And it's kind of like completely different level of how to answer those questions, right? So essentially, what is the policy? What is the meaningful, secure course of action? It gets complex. So in both of these systems and in my microkernel construction, these questions have to be somehow answered, because in my microkernel construction, I kind of add those errors. Think of them as pointers, which allow you to communicate to specific parts of the system, right? And again, there are two schools of thought, and they kind of conflict. And I mean, I kind of bounce between them, I guess. One school says, okay, starting from nothing and adding those edges to this graph will give you more secure system. But in practice, you say, look, it doesn't really give you a very good answer, because this error, for example, answers the question whether you can talk to a file system. But within the file system, there might be like a multitude of files. And so you need to like distinguish whether you can access a specific file within the file system. And this error it's kind of like a different level. It's base communication versus some semantics of what you can access. So there will be a layer of access control on the top. Some people start pushing, okay, guys, no, it shouldn't be like this. You really should have an error pointing to a concrete file. They push this model to the extreme. So, and then you can only access this file And then it becomes hard. So it's hard to build because this fine granularity is harder. So there is no real clear solution, whether you start with a C Linux or start with this microkernel construction. The only argument which seems to be clear is that if you start with the microkernel, in which by construction of those subsystems, you build them in this isolated manner, possibly being able to verify the microkernel, verify shared subsystems, it at least gives you the tools to construct a system in which you have isolation as a base primitive. And then on top of it, you can allow, like you can add permissions to communicate if you like, right? If you start with a mess like Linux kernel, no matter which access control framework you implement, you cannot isolate something what is already shared. Essentially, that's the philosophical observation. The question of policy, how to implement a meaningful policy, I think exists in both systems and is still unanswered. There is no easy way, to still looks like to me to write those policies. But essentially, if you take a mass, which is a Linux kernel, try to say, now I will like partition the Linux kernel kind of like logically with this AC Linux primitives or OpenBSD primitives, there is always some kind of like shared state, like allocators are not fully partitioned. We just looked at the scheduler. It's like one global scheduler, like which cannot schedule groups of processes and stuff like that. So that's kind of tough, right? Does this help a little? So the policy is still, questions still exist, but there is also another interesting observation about those microkernel systems. If conceptually, since they are very, very minimal to begin with, you can end up either with like a mass, with a Linux style mass, where security becomes again a super challenging thing, because you say, look, this is a user one, this is user two, they somehow share a file system, and you have to convey the fact that those are different users. But if you say, look, if I'm building an embedded system like an insulin pump, there are no users. There's just one system, and I have a formal specification for what needs to happen. It has to deliver insulin so often, so dosage and dosage. There is a network stack. It has to communicate, maybe like provide the reading of whatever the sugar level in the pod, right? Then you say, look, with this very small system, you can build something relatively simple, in which this access control, this simple version of access control, suddenly becomes meaningful, and can you achieve like an end-to-end guarantee? It's way harder to kind of put this end-to-end guarantee on top of a complex kernel. So you can use this Lego-like construction to build something simple, versus if you already have a pile of something, it's much harder to make anything useful out of it. So kind of simplicity plays nicely for simple systems. For complex, probably everything converges to some unsolved space where we don't know the answer. Okay, any other questions about? Okay, but the subject of today is the following. The subject is actually answer all of these questions, like answer what is how we solve naming, how we solve for access control, and not surprisingly, if we want to communicate, how we physically build communication, or it's called interprocessor IPC, interprocess communication. I mean, like I use the term IPC, whether it's virtual machine or anything, just like think of it as where you have to communicate between address spaces. So, but at least we have this access control. Again, we'll get to it. Like, let's start with the IPC. So how to build communication, right? And then we will more naturally will go, I think we will be able to solve naming and provide one solution of access control, which is centered around those pointers, right? And we'll be calling them capabilities. Okay, so kind of again, back to building. So we kind of understand what the end result is, what we want. We want to be able to build those systems which are composed of a bunch of processes running on a microkernel, right? So now the question is like, what is this communication primitive which we want to build? Like at the level of, privilege, ring privilege changing and stuff like that. We can use Y as a basically. So how can we build it? My regular picture. This is ring 0. This is ring 3. We have 2 processes. And just to make example concrete, imagine this is a server. And this is a client, kind of like a file system and a process, right? And the client wants to invoke a function provided by the server. How can we implement this abstraction? How to build it on top of your microkernel? You probably already built something like this in your past or parts of it. Okay, do we know any communication mechanisms? What's the communication mechanism in x6? Pipe, yeah, so how does it work? In x6 we have one, which is pipe. Okay, can you give us an overview of what pipe is? In x6, just to make it great. At some levels, you say, look, there will be a file descriptor table, and one of these file descriptors points to a logical pipe object, not logical, data structure pipe in a kernel, right? And then what? How do they communicate?
So one process text we can the other reads from the other.
Okay, so agree with this. So pipe, like data structure in a kernel, has a allocated region of memory. In x86, it's 512 bytes, which is logically implemented as a ring buffer, which essentially says, okay, I will maintain the pointer to currently written elements, right? And so imagine this guy can write. It has a pointer, right pointer to the pipe. So essentially, when it invokes a syscall here, and it's a write syscall with this specific file descriptor, it can pass a buffer and a len, and whatever bytes are in a buffer will be added to the pipe, right? So I will mark them red just to make sure that we understand that those are new, right? And this pointer, which previously was pointing somewhere here, will be pointing to this, to the last byte of this producer, of the producer consumer read. And the other guy does something like a read from a read end of a pipe. It also provides a pointer to the buffer in the LAN. And essentially it says, look, I want to pick up some number of bytes from this pipe buffer. And maybe it will, like, there will be a pointer which points to the produced thing. You can maybe pick up like 2 bytes, for example, and these 2 bytes are copied by the kernel in this memory, right? So pipe is fine. So like, again, so how can we build something like this? Like technically we can build exactly the pipe. So essentially syscall passes a collection of bytes as a buffer. We add them to the buffer in a kernel. That's totally fine. It sits there. Then the other guy says, okay, I want to read something from a pipe, reads those bytes, return. So how on top of this we can build this invocation of a function?
Question. So we don't have file system in our kernel.
No, yeah. So for example, imagine this is a process and this is a file system. And this function is actually like a read from this file system. The pipe itself has no connection to the file system, right? So it's a communication primitive which works like this. It allows you to put bytes from a process to another process, right? Makes sense. So how do we build this read?
Syscall.
But what do you mean a syscall? Now it's a call between the client and the server, right? What is
still talking IPC6?
Well, you can imagine it's your kernel in which you build a pipe. It's the Rust kernel.
Well, we're building a microkernel, so it's not a syscall, so it needs to go through not through the kernel, but directly between the two processes.
Ideally, but can you? Because that's essentially what I'm trying to get to, essentially. Can you go directly like this?
Maybe if each side owned their respective buffers.
No, I mean, partially you're correct. You say, look, if we somehow say allow those guys to share a region of memory, right? We can put this buffer in this region of memory, and instead of like going down in the microkernel, going through this pipe, we will just blindly write into the shared memory, and maybe just we'll keep spinning a little bit, synchronizing, waiting for this guy to pick up the request and give us a reply, right?
Question. So will the mapping for the address space of the file system be in the process P page table? Essentially, how do you know where to go?
Yeah, that's a good question. So hold on. And like in this example, we assume that the memory is shared, right? Obviously, it's a chicken and egg problem. And you ask the question, okay, how can you allow two processes to share a region of memory? And you kind of go back down to this, like you need to design an interface which allows those two guys to communicate to begin with, to at least negotiate sharing a region of memory, right? It can be done differently, but maybe we can build a unified inter-process communication mechanism which allows one process to kind of send a page to another process, and this guy receives and the microkernel maps the page. So like if you're sending a page, the behavior can be map a page, right? It's not super hard. So like don't get confused. But okay, any questions about this? Let's first, instead of like instead of going for this, it's called asynchronous communication, as you say, we'll get to it in a second. Let's just solve the synchronous case. And just for simplicity, let's just learn how to communicate scalar values first. No, like it's almost here. So you say, look, if we have a concept of a pipe, like, then it almost works for us. No, confused? Okay, let me explain it differently. So, like, the reason I brought up a pipe is that I was thinking that you guys will pick up on this idea that, okay, if I see a pipe, I can just implement it in my microkernel, and then we will just take a route of optimizing the pipe, and essentially we'll understand why the pipe is not ideal. But we can take a slightly different route. We can say, look, imagine, I mean, we know how to build syscalls. First of all, like when we start two processes, right, they are isolated. So they have their own address spaces in the microkernel, right? So this address space is completely isolated from another address space. Nothing is shared, right? So it's kind of like it's okay, that's how we wanted it to build. And it totally makes sense. Which means that the only way to communicate, you cannot go straight between these address spaces, right? At least initially. The only way to communicate is really to go through a microkernel. So kind of like pipe style communication. Say, look, we're gonna build we already have a syscall abstraction, whatever the sysenter, which drops us from ring 3 to ring 0, right? And we can implement something like a send system call. Send system call takes an argument, which let's call it initially as a file descriptor, and some message, right? So let's just, for simplicity, like again, maybe it's just a fixed byte message. Maybe it's 64, maybe 128, right? When you do a syscall, the microkernel says, okay, sure. Instead of having a pipe object, we have a slightly simpler object. We'll call it an IPC endpoint. Oh, right, EP endpoint, right? And essentially, the microkernel can say, look, if someone is waiting on this endpoint, I mean, we have a couple of design choices. We can either temporarily copy this message into this endpoint, and this guy immediately returns. And that's one design choice. Or another design choice is to say, look, we require, in order for this guy to return, for the sender to return, we want a thread from a different process already waiting on this endpoint with the receive system call. And what it gives us is that if this guy is already waiting, instead of like doing an intermediate copy of a message into this endpoint space and kind of like a pipe buffer, we can, in a microkernel, when we land on the synthesis call, we check this endpoint, say, okay, someone is already waiting. We have this pointer to memory which implements a message, and we can immediately copy from one address space into another. And arguably, it will save us just a couple of cycles. But still, people were so obsessed about it that they decided, let's do it, right? And this endpoint is kind of like a pipe, but can hold only one message, right? And we have the following semantics. So you send, and if no one is waiting, you got blocked. You receive, and if there is no message waiting for you, you get blocked. So someone has to get blocked first. And then the second one immediately gets the message gets delivered. And the question is like, what about scheduling? What do we want to do? Because if our use case is to implement this call, so logically is what we want is that when thread 1 did a send, and imagine thread 2 was already waiting, we want to really schedule and start running T2, because it's kind of like T2 will implement the logic of who, and by the time it's ready to return, it will just do a send message back to this endpoint. And if we slightly change this system call, we say it's send and receive, then this guy immediately gets unblocked. We copy the message back, and this guy actually, it kind of like mimics the invocation of a function call, but across address spaces. Make sense? So, and we can say, look, okay, we can have this different versions of send. So it's send and don't expect receive, or we can say something like call and reply. Forget how they, okay, let's just call them send and receive. Send and receive. We can do a receive system call, but we can also do kind of reply and receive. You need that in this one. For those. If we implementing like a server which constantly calling on incoming messages, then it will be always dropping. Instead of doing the receive here, it will always be doing reply and receive, meaning that it will answer into this endpoint and get back, and it will stay there, right? Waiting for it, right? Does this make sense? So this is roughly an interface which is implemented in the a CL4 or generally L4 line of microkernels. It's also called synchronous IPC because you say, look, it's kind of like your execution migrated from one address space to another, despite the fact that you're kind of involving two threads, logically only one of them is running, right? So, and they are synchronizing on this endpoint, right? What are the advantages and disadvantages of this approach? What is good about it? Or why I was saying that instead of building a pipe, I'm arguing that we have to build these endpoints.
Like there's no extra buffers required. So this endpoint is just metadata for the processes.
So we kind of, what you're saying is that we're avoiding an extra copy into, yeah, I agree with this. Also, it's more tuned towards implementing cross-address space invocations, right? Because in pipe, you leave a message in a pipe, but you never really know when it will be served or anything, which is fine. Maybe it makes sense in some cases. But we also leverage the fact that we kind of changing the scheduling slightly around the endpoint. We say, if the receiver is waiting, we context switch, and we really have to context switch, because we changed the CR3, to point to a new address space, right? Change, we do context switch, but it's a context switch which is not triggered by a timer, or it's more like a yield on an endpoint. You say, look, they're immediately yielding here. This guy will run, reply, yield back, and stuff like that, right? So that makes sense, right? What is not ideal about this? So, but the high-level story, it's tuned for implementing this address space, cross-address space invocations, right? So it's kind of like a syscall. If it's a file system, you would normally invoke a syscall, but we dispatch on the endpoint, and instead of solving, executing a syscall inside the microkernel, we go up to the server process which is connected to this endpoint, right? So that sounds reasonably nice, but what is not ideal in this method? Okay, worse, you say, if Google hires you, just tells you to build an Android kernel like this with this send and receive primitive, will it fly or not? And what will not fly?
I have a question.
Yeah.
So it seems like this would work great for two processes, but if you have a lot more than two, let's say that point.
Right, that's a great question. So let me explain it. Imagine a file, I call this thing a file descriptor now. Imagine each process has a file descriptor table, or we can call it endpoint table, right? And let's even write endpoint here. We pass a number, 5. We resolve it through some data structure, saying that entry number 5 points to an endpoint, right? But obviously you can have multiple. So entry number 6 will point to a different endpoint microkernel object, and that one might lead you to something like a network device, right? So this was a file system, this was a network device, right? So this kind of solves half of this problem. The second half is that if it's a file system and it has a single endpoint, so it's it also has a file descriptor or endpoint table here, and it's since number 3 connects to the same endpoint, of course, it might, you can structure the system differently. And you can say maybe an endpoint is one-to-one connection to a client. But then you face this problem of a poll system call, right? Because poll means that you don't really know which endpoint is ready and who will send the message first. So ideally, you would like to share this endpoint with a bunch of processes, right? So there will be another process, whatever, if this one is P1, this is P2, and this one also can do a like invocation of foo by sending a message into this endpoint. Then you can like uniformly receive, like it's your poll essentially. You say, when I do reply on this one, my next message can come from a different client, right? And so which means that you probably want to implement some kind of a queue here, queuing the clients, because you might have they might run in parallel on multiple CPUs and they all do send, and they have to be queued here, and this guy like just periodically keeps up, does a reply. But then you say, look, but what if this doesn't catch up? And really it has to be a multi-threaded system. And then 2 threads of this guy receive from this endpoint, right? At this point, you might run into a problem when you have to somehow kind of match sends and receives, which I cannot immediately explain. So how does it work? So for example, like imagine you collect a bunch of receives, and those guys are waiting somehow because they did the send. They're waiting for replies, but maybe those replies can come out of order as well, because if multiple threads are picking up something from this endpoint, like 2 threads, it's obvious that, like even a single thread can reorder replies for whatever reason. Maybe it takes longer. And then you have to somehow match whoever did the send. If this is a send and receive invocation, you have to match it, right? So you have to solve this problem. A typical elegant way, almost like a language way of solving this problem, is that as part of the send and receive invocation, you pass another endpoint, and it's like your private one. And when you do a send receive, instead of waiting on this one, you actually start waiting for receive on this one. And this endpoint reaches this system, and then you can specifically answer back into this endpoint. So it's kind of like connecting clients and receivers. And if you're very careful, you can optimize this scheme so it like introduces minimal overhead. And I think this is how it's done in those CCL4 microkernels. Although in our goofy microkernels, I don't think we do it, which is like, yeah, not ideal. But it's a real problem, and it's like you got the point. It's kind of almost like this, like if you like, it's passing a continuation to a server saying, okay, here, like next time you're ready to answer it, like continue with this endpoint. So I didn't want to immediately kind of like jump into it, but it's a good question. But this kind of explains how it works, right? So, but there is some complexity. So it's like, it's a little like starts very easy, but then if you have multiple senders, multiple receivers, you have to deal with them. And like an elegant solution is not always like obvious. But okay, sure. Let's imagine for a sec still no multiple senders and receivers, but just one sender, one receiver. So what's not ideal with this? Again, remember my Google story asking you. Okay, what's the bottleneck of this communication primitive?
Scheduling.
Wow, why?
Well, it seems like the first thread dumps something into the endpoint, the second thread needs to pick it up, and unless the second is marked as now unblocked, then you may be waiting longer than necessary.
Hold on. But maybe you missed what I was trying to explain. The requirement is that in an ideal scenario, the receiver is already waiting on the endpoint. Okay. And so you immediately know. So it's like, it's a small constant. It's just a pointer to whoever is waiting. If no one is waiting, then you get blocked, and then you enter the scheduler and you pick someone to run. And you're right, it's not ideal. Maybe you'll not reach the server, but in an ideal use case, the server is already waiting. And so your scheduling is essentially kind of like you don't really make a real scheduling decision. You just do a yield to the server, and the server starts running, right? So that seems not a problem. Although in Linux, yes, building this will be hard and expensive. But in a small microkernel where the scheduler is simple, and you say, I will integrate this idea of IPC with my, like with yield, basically. It's kind of like almost you donating your slice. So this process says, okay, and you can play with those games saying that, okay, who is actually, it was explored as well, but okay, let's not go there, but essentially you can like continue running on a slice of this, a time slice of this, of the sender. But really, what takes time? And like, first of all, is it fast? So how long it takes to invoke a null function? Let me ask this question.
So that the context switch to 0.
You have to context switch to where? Yeah, so you have to invoke a syscall. And I said, okay, maybe it's roughly, I think like round trip is roughly 150. So let's say 75 cycles to go in and back. So 150 here and 150 here, right? On Intel. What else? We'll just speak the round trip time.
We're still doing a copy of the data.
Yeah, so but maybe it's small. Let's say even like 256. We can fix the number, right? But not a lot of cycles. Let's say for copying, I don't know, like let's say 10 cycles or something for copying the data, like maybe whatever, 50 cycles for whatever, saving, restoring registers, doing the context switch. What else? What is expensive? Well, it turns out that actually reloading CR3 is actually reasonably expensive. By the way, I forget if I ever talked about it, but are you familiar with TLB, translation loop-aside buffer? So TLB caches results from virtual to physical, right? In the old days, like imagine you build a cache for process one. Because when you switch between one process to another, you have to dump the cache because otherwise the virtual address from this process will go to a physical address which belongs to this process, right? So you have to flush the cache and refill. And it was quite expensive. These days, all these mappings also have an ID, a process ID tag, which means that the mapping is only valid when the currently running process ID tag matches this ID, right? And so essentially you can have like, it's called tagged TLBs, which means that you can have like same address, 0, for example, mapped to different physical addresses, but the ID of a process will be ID process 1, ID process 2, and so you don't have to flash them on context switch. And yet this thing is still expensive. Roughly speaking, you have to switch the page table once, and then you have to switch page table back again. And I'll make up the number roughly, maybe another 150 to 200 cycles for one switch. Plus, I mean, it's hard to measure, and I didn't measure a long time ago, but essentially numbers started like because you need to do this twice, right? So roughly speaking, everything is twice. So it's like 150 plus 50, 200, plus another 200, 400, plus 10, what is it? Already confused, 400, 210. So we end up doing something like, let's say 800 cycles. And it's very optimistic. So maybe 800 to, let's say 1400 cycles, right? So your normal function invocation was taking, let's say, 5 to 10 cycles. Suddenly it takes 800 to 100 to 1400 cycles just to send a tiny message, right? Okay, so that's not ideal. So this is essentially the overheads of entering the kernel, like saving the context, switching the page table, surprisingly expensive. Then also some overheads of like polluting TLBs, because it's kind of now you say, like some of these entries, you will be a capacity like miss, like you say, look, I need to add another entry, so I will just like cross one out, and it pollutes the TLBs because it's like kind of like shared between two processes, two address spaces, and essentially when you come back to this one, it says, okay, wow, I lost this entry, but and of course it's all like mostly recently used policy or something, but still you can see performance degradation, not just even measurable directly through context switch, but through pollution of caches, TLBs, stuff like that, right? Because you share L1, L2, caches are probably less impactful. But overall, like even this number is a little scary. So you suddenly say, look, I have to pay 800 cycles to, let's even like if it's a, let's for a second imagine it's a network interface, network device driver to just send a single packet, right? Okay, so this IPC mechanism works and is reasonably good for certain scenarios where you like, you know, your invocations, cross-domain invocations are not very frequent, but it doesn't really work very well for cases where you have to send like millions of packets a second, right? So how can we improve? So what is wrong with this and how we can change? Make sure that we can send a lot of small packets without the overhead of 800 cycles. You can batch them together, right? And sure, you can say, look, this message, imagine now we say, look, we tried it, we ran it. Now imagine it can be like a compound, some kind of a scatter gather array, and this guy like points to a bunch of different messages, right? And you can like do the same trick, right? But now you kind of amortize the cost of entering the kernel over like, I don't know, a batch of like, let's say 32 one kilobyte messages, right? By the way, batching works well only in certain workloads because it increases the latency, right? And so like realistically, even batch of 32 for a network interface is a little tough. So you would prefer something like batch of maybe 8 or 10, 8 or 16, right? Because latency is growing, and often you simply don't have enough, you know, asynchronous computation to accumulate a batch. Some workloads naturally have them, but some don't. Like if you read a large file, no, like it depends. You can always try to restructure the computation. Okay, that's fine, but still, what's not ideal in this with this batching approach? Although we kind of improve it. What's your next optimization? DMA. Well, for DMA, okay, what solution are you trying to solve with DMA?
So you allocate like maybe large pages, and your process can directly write into those pages, and your NIC can directly read them.
Hold on. Like forget about a NIC for a sec. What you were saying is that I wanna have some magic device. I bought it from a company. This device actually existed. And it will somehow do what with those packets? You want them delivered from here to here, right? So right now you say, look, I have to go through kernel. Kernel will do a copy from here. The sender presumably will provide a scatter gather list of receive buffers, and the kernel will just essentially will copy from one into another, right? It takes CPU time here in the kernel, right? Because you have to copy more. If you have a magical device, then maybe you like ask this device to essentially DMA those packets. So you talk to the device instead of a kernel. You say, wow, I will like instead of sending down here, you send directly to this magical device, and this device will read them from this memory, use its own processing power, and write them into this memory, right? So like, but CPU is not involved. So maybe we yielded the CPU, something else is running, but at least we're not wasting cycles of the CPU on this, right? This makes sense? This device existed. I think it was called Solar Flare. At least one of them, or maybe it was like a prototype. So there was a point in time where buying this device was cheaper than buying more CPU cores to essentially just keep like, because someone has to copy, and actually DMA is more expensive operation because you have to go through a PCI bus, so it takes you even longer. But still, you know, like, I mean, maybe device failed because it wasn't actually cheaper, but at least it was marketed as the way to offload from the CPU to a device to do this copy operation. So essentially, think of this device as like copying one memory to another, but there is still a CPU here, maybe some kind of an ARM core. And this, if it's significantly cheaper than buying more cores on the main CPU, it works, right? Okay, but we at least identified the problem. We said, okay, we kind of don't want to copy data from one buffer to another, right? And okay, so what's the elegant solution? What's another solution to avoid this copy without buying a new DMA device?
You pay this 800 to 1400 cycle cost once, and the kernel creates a physical memory allocation and maps it separately to the virtual address space.
Correct. So what you're saying is that, okay, sure, we got it. We learned how to send small messages through this synchronous mechanism, but really it doesn't scale very, very well for large messages. And so we want our IPC to support a slightly different form of invocation, which will look like this. We can send, let's say, a page, or like an array of pages, but one is enough, right? We can send it multiple times. And like somehow magically in this message, which we're passing into the kernel, this, instead of a scalar value, we mark it that that's a page, right? You still drop into the microkernel, there will be still an endpoint. And if receiver, and you can play an application level protocol, maybe like the first message which the receiver expects to receive is something like a pen-shaped hello message, but the second message which it expects to receive is a page. So it says, okay, got it. I'm actually ready to receive a page. In my message, I provide a pointer to a virtual address where I want this page to be mapped, right? And then this mechanism is the microkernel. Instead of like copying everything, it says, okay, got it, guys. I see that you're trying to send a page from one address, from one process to another. And so I will do that. I will just, I get it. This page is already allocated. For example, it has a corresponding physical page. And so it has a mapping in this address space. And if you're sending it, I will just map it, getting it to this address space at this virtual address. And so this is now the page which is mapped in both address spaces, right? So roughly speaking, and we can send multiple pages, which allows us to set up a region of shared memory. And now we can, in order to send something across, we can, for example, say, look, this scatter gather array, we don't even have to drop into the kernel. This is closer to what Palia was saying. But instead, we maybe can just copy those messages into this shared area. Maybe there will be some kind of a metadata region which implements the ring buffer, and the ring buffer points to those. We update the ring buffer to point to those pages, and then this guy doesn't even have to drop into the microkernel, but just simply has to be monitoring this ring buffer, right? And then to receive those pages, you can, for example, say, look, I will have allocate some receive buffers, and I still do a copy into those receive buffers, right? So that improves because we don't have to go into the kernel every time we want to send something. So we're saving at least this 800 cycles, right? However, what's the gain? What's not ideal again in this scheme? Although, like, logically, this is what people are doing, but still, what's not ideal? We're still batching. We can batch, or we can have packet one by one. That's a good question. So, like, technically speaking, we don't have to batch as much, right? Because we can add if there is like a ring buffer, then which maintains like producer and consumer pointers, we can simply add one by one, but that may be touching the producer pointer, which might be bouncing a cache line between the cores, and depending on whether this introduces enough bottleneck, we'll talk about it in a second, that might be prohibitive or not, but maybe we don't have to patch, right? So now we can, since we don't have to pay the price of 800 cycles, right? So we just like adding a producer pointer is probably like just a couple of cycles in a good case, right? In a bad case, it can be worse.
So now it's just like the only problems I'm seeing are ordering problems, like your memory.
But like imagine you're like either total store order, or maybe like you use enough barriers, and then you just every time you update the point, you first obviously finish like adding data to the packet, maybe a barrier. Maybe you can wait until you update the producer pointer because it's not visible to the.
And I feel like it's fine, like we just implemented mmap.
Correct, and essentially this is partially how virtual machines communicate, but you still like, you have an overhead of 2 copies, one from here into the buffer, and one from the buffer into the receiver, right? And if you're sending megabytes of data, like copying to 124 kilobyte packet is roughly maybe 50 cycles, maybe even less if you carefully optimize, but still it starts adding up, right? And so it depends. So it depends on what your workload is, what size of this messages is, but you still have overhead of copying, and it's not ideal. The second thing is that this guy has to constantly pull on the buffer, right? Because if we say our default protocol is just notify the receiver by advancing the producer pointer, then, well, this guy has to constantly keep polling, right? And it's okay if it has some kind of natural work to do and it occasionally checks the buffer. But what if this guy is totally idle? Then what do? We either burn a core, and ideally, actually, we have to run on a different core to begin with, right? Because otherwise, this guy still has to like batch like 32 packets, but there is nothing else to do, right? It has to receive replies. At this point, it has to yield, go into the kernel, do a context switch, and then we again paying the price of 800 cycles. So ideally, this scheme works well when you're running on 2 different physical CPUs in parallel, right? And then just like kind of have enough work that like, and work is evenly balanced. So this guy is process 1 unit of work, picks up 1, process 1, picks up 1. Because otherwise one of them starts being idle. And the question is like how to notify this guy. So essentially let it be in this, literally in a while loop, waiting for the producer pointer to change. Is that the game, or how do we want to go about it? And yeah, so people did all these tricks, and so like probably the most sane strategy is say, look, I will spin for some amount of time, and then I will go to the endpoint. I will start sleeping there, waiting for a synchronous receive, so I don't have to burn the CPU, right? So, and this guy says, okay, I update the producer buffer, but if I believe that this guy went to sleep, I will send an go and send a synchronous message, right? Make sense? But kind of this flavor of, hey, wait, we finished at 20, right? This flavor of IPC is essentially heavily used in virtual machines. Like this is how virtualized device drivers communicate, right? So essentially this idea. Hold on, let me stop here and we'll come back next time, talk a little bit more about IPC and move on to access control essentially. But yeah, so we'll see you Monday. So I actually plan to teach both Monday and Wednesday next week. I apologize for Wednesday because I assume Thursday is the Thanksgiving, right? But I will be here. And the reason is that, okay, I traveled and I